Welcome everyone, and thanks for joining the Time Series Connect Spring 2026 webinar series. I'm Yao Zheng, Associate Professor of Statistics at the University of Connecticut. This series is co-organized with my colleagues Dongjin Song from the School of Computing and Junbin Huang from the Department of Economics in partnership with the Business and Economic Statistics section of the American Statistical Association. The goal of this series is to bring together researchers, practitioners, and students with shared interests in time series, and to create an open and welcoming space for learning and discussion across disciplines. Now it's my pleasure to introduce our inaugural speaker, Dr. Peter Craigmile. Dr. Craigmile is a professor in the Department of Mathematics and Statistics at Hunter College, CUNY. His research interest includes time series and longitudinal analysis, spatial statistics, and spatial-temporal modeling. He is currently interested in developing statistical methodologies for the statistical inference and theory surrounding stationary and non-stationary non-Gaussian spatial and temporal processes. He works on building scientifically relevant hierarchical statistical models applied to areas such as climate science, environmental health, psychology, and public health. He is a fellow of the American Statistical Association, the Institute of Mathematical Statistics, and the Royal Statistical Society, and an elected member of the International Statistical Institute. I'd also like to mention that Dr. Craigmile has been very active in organizing online seminar series over the years. I recently discovered that actually one of the webinar series he organized dates back to 12 or 13 years ago. Which truly makes him one of the pioneers in this space, at least I think in the statistical community. So it feels especially fitting to have him as our first speaker to kickstart this new initiative. With that, I'll turn it over to you, Dr. Craigmile. Feel free to take it away and share your screen.
Okay, wonderful. Well, I'm very excited to speak first, and thank you so much for the invitation. And I certainly look forward to any questions that you may have as we go through. And also, I'll say a little bit about, just thinking a bit about, time series analysis and what we typically do, and then maybe what we would like to do in practice. And I'm going to keep this, although I'm going to talk about some fairly, sophisticated statistical models, the one thing I'll say here just to get things going is that we're just going to imagine that you have one time series that you want to model, and what would you do there? So we're going to focus on modeling non-stationary time series. We're going to look at using what's called locally stationary basis processes, and this is joint work with a former PhD student who's Shrein Ganguly, and this was funded by the US National Science Foundation and the National Cancer Institute. So, if you were sitting in a time series class, right, and you were learning about time series, after you've got past the part where you say, let's look at some example data sets, you would probably spend quite a bit of time learning definitions, right, about what a stationary time series is and why that's useful for statistical modeling. And so I'm just going to remind you about that story. So typically, we often start with something called a weakly stationary process to model data. And, while stationarity might not be a good, true in practice, it's a pretty good approximation for lots of data sets. And really the idea is that, we're assuming some sort of invariance over time. And so a weakly stationary process has a constant mean and variance, and then it has a covariance function or autocovariance function, which basically says we're going to look at the covariance between xt and xt plus h. And the part that makes it stationary, in addition to having the constant mean, is that the covariance function only depends on the lag. So it only depends on h here, how far apart we are in time. Okay, and as soon as you have a stationary process, you can basically represent a stationary process in one of two ways. You can either talk about means, variances, and covariances, or you can talk about it in a spectral representation. So the easiest way I think about this is we basically say that a stationary model can also be written in terms of sines and cosines, okay, in a special way. Okay, and this is the way that we often do it with an integral representation. I'm not going to worry too hard about this for the moment, but just to realize that when you write it in this interpretation, you get this function here that's called a transfer function that depends on frequency. And if you take the modulus of that function squared, you get something called the spectral density function of the time series. And this gives you a way of viewing dependence in terms of amplitudes of the sinusoids that represent the time series, rather than thinking about covariances. And a lot of time series analysis is really about either thinking about covariances or either thinking about spectral density functions. And you'll notice that come through as a theme in my talk, okay? All right, well, the truth is that if, just because things are stationary doesn't mean that that is actually true, right? And even in an intro stats class, you would spend a lot of time talking about things that are not stationary and what features you would see, like trend and seasonality, or maybe differencing to start to think about how to make things stationary, and that leads to integrated models. But in lots of cases, we don't imagine that things are just exactly, that I can capture things in the mean, or I can difference a process to understand what's going on. But maybe what's going to happen is that as you go through time, things are going to evolve continuously, right? Okay, so I don't imagine that, for example, if I look at the spectral density function by frequency, and I imagine working my way through time, it may be that things aren't constant in time, but in fact they evolve, and basically the dependence in the time series changes. And so the question is, what can you do in that situation? Well, the truth of the matter is that people have known about this for a long time. And you can go back to papers of Priestley back in the 1960s, actually, a very long time ago, where he talked about evolutionary spectra. But the one that kind of jumped on the kind of definitions that we think about are due to Dalhouse, and they're called locally stationary processes. And so a locally stationary process looks like this. It's basically a time series, okay, again, indexed in time. We'll come to what the capital T means in a minute. But basically what it says is it has a mean that changes over time. Okay, and then it still has this kind of representation in terms of sines and cosines. Okay, it still has this transfer function. Okay, but the difference from before is that the transfer function is going to change as we go through time. Okay, but it's going to change in a very specific way so that the changes that we see over time are smooth, okay, rather than just jumping around. Okay, so a locally stationary process, another way we can think about it, okay, is basically to say that if you look in a small window of time, okay, that the process looks stationary. But as I start to move along in time, okay, the properties of that time series model change. Okay, so what's nice about a locally stationary process, or an LS process, is it captures slowly varying departures from stationarity. Okay, now Dalhouse was very smart, and he wrote down all the conditions under which this is true. The way that it all has to work is that there's this capital T that appears, right? And the capital T basically says that if you zoom in time, okay, that you can imagine rescaling time, so taking the time index divided by this capital T. And what's going to happen is that you'll always think about the properties lying between 0 and 1. And so people call that rescaled time. And so what happens is if you imagine observing more and more data, you actually get more and more information about what happens in this rescaled time. Okay, and by making that sort of assumption, that's what allows you to have nice statistical properties. Okay. So here's this need for rescale time. So they're defined over a rescale time. That allows you to do some asymptotics, infill asymptotics, but it also allows us to think about the model interpretation. So I'm going to give you an example. So let's suppose that we look at probably one of the simplest time series models out there. It's called an autoregressive process of order 1, but I'm going to sneakily change it just in one way. So I'm going to say that the current xt depends on the previous xt minus 1, okay, through phi t times by xt minus 1 plus an error, right? Now, the phi t is called the autocorrelation parameter. In an AR1 model, this would be constant over time, and there'd be some conditions for when it's stationary. Okay, now imagine that it evolves over time. So I'm going to make things quite crazy. I'm going to do linear. Let's suppose that it's phi t is a plus bt, and we'll say that b is positive. So that as t goes to infinity, phi t goes to infinity. Well, the problem with this is that the model is no longer stationary. Okay, so this is an example where I didn't consider rescale time. So what I'm going to do instead is I'm going to take this phi of t and I'm going to rescale it, okay, by basically introducing this capital T that I imagine observing over. And what we're going to look at is that we're going to take phi of t over the capital T. So that basically takes us into rescale time. And if I make sure that this function of rescale time in magnitude always lies between 1, okay, then I get a locally stationary process. Okay, so basically what happens is this model explodes, right? And you're not stationary anymore, whereas as time goes on, whereas this model always in a small window stays locally stationary. And so this model behaves nicely and has nice theory about it. So this is known as a time-varying autoregressive process of order 1. Why is it order 1? Because it only depends on the previous time point. Looking good so far? Okay, so if I think about this function here, phi of t over t, well, let's just ignore the t over t and just imagine we're looking at the rescaled time, right? Remember, rescaled time was just, let's set some u up to be this capital small t over capital T. Then imagine that I want to look at the form of this function, okay, phi of u, say. Okay, now I told you in this case that the values in magnitude of the function have to lie between, well, in magnitude have to be less than 1. Okay, so the question is, how would I model that over rescale time? Well, we want to find time-varying parameter curves, so phi of u's, say, okay, the model, so that we guarantee that something stays locally stationary. Okay, and one way to do that is by writing down basis function expansions of these functions. So here's an example. So in the time-varying function, I'm going to take logit of this transformation of phi, and I'm going to write it as a linear combination of basis functions. Okay, so you give me some smooth basis functions, I give you some coefficients beta, we'll take a linear combination of them, and then through some transformation, I'm going to define my phi function over rescaled time. Okay, now I know what you're maybe thinking here. The question is, why on earth did I write down a much more complicated function? I didn't just say phi of u equals the basis function. Okay, well, if I go back again, I want the phi's to lie between -1 and 1. And so what we're going to do here is we're going to transform the phi's, okay, in such a way so that we're guaranteed that the phi functions, okay, lie between -1 and 1. But then when I transform them in this way, I now live on the real line. Okay, now we do this sort of thing in other statistical models right out there. For example, if I was modeling probabilities that lie between 0 and 1, okay, I might do a logistic transformation, right, to transform them on the real line to make things easier to model. Well, this is just an example of me doing this now, but I'm doing it for the autoregressive parameter curve that changes over time. Okay, so more generally, we can write down a general class of models defined using these basis functions. And we're going to say that a locally stationary basis function is a locally stationary process, okay, where I'm going to have this time-varying transfer function. Okay, so what does this mean? Well, I'm going to have basically something that is a function of a heap of parameter curves. Okay, so we'll call them zeta 1 up to zeta j. And we're going to have a parameter that tells us about the frequency. And what's going to happen is we're basically going to write down a time series model, okay, through these m functions, okay? And we need to make something, to make this locally stationary, we need to make a number of assumptions. So the first thing is we're going to assume that the function is continuous and differentiable, right? And we're going to say that it depends on these parameter curves. Okay, so what does that really mean here? When you write down a transfer function, this basically says that you're writing down the time series model. Okay, the time series model is going to depend on local time and is going to depend on frequency. Okay, so the frequency is going to tell us something about the covariance or dependent structure in the time series. And through the local time, that's going to allow those properties to change over time. You can see it's controlled by these time-varying parameter curves. Okay, now we're not finished with the model yet. So I have these parameter curves defined over rescaled time. Now I have to say, how am I going to write down models for these parameter curves? Okay, so we're going to write them by taking transformations of these parameter curves in terms of basis functions. Okay, so we have to make a number of assumptions. We're going to assume that the things that transform the parameter curves, or we'll call them linked functions, we'll assume that they're continuous and differentiable and one-to-one. So that makes everything nice in terms of statistical properties and in terms of uniqueness. We'll define a heap of basis functions, okay, for where these parameter curves are going to go. Okay, and then we're going to have a bunch of model coefficients. Okay, now if you notice, I did this for each one of these parameter curves. Remember here that when I write down the time-varying covariance or time-varying spectral properties, okay, it depends on these J curves, right? And so I have to do this for each one of those J curves. And so we'll just collect together all those parameters into a big vector beta. Okay, so this is our model. Okay, now there's a lot of properties you can write down. Okay, you can show for this version of the model, okay, that the expectation of the process is just the time-varying mean. You can calculate exactly what the time-varying spectral density function is. Okay, so you take this transfer function, you take the modulus squared, and that exactly gives you the time-varying spectral density. So this is a measure of basically sines and cosines in a local behavior in time over frequencies. You can also work out how the covariance changes over time. So we can define a time-varying covariance function by integrating this time-varying spectral density function. Okay, now a lot of this is really just using results from Dalhouse, okay, that shows you that if you have local stationarity, then all of these properties come out. In time series modeling, we often distinguish between processes being short memory or long memory. So short memory are processes that have a covariance that decays over the lag very quickly, okay, typically an exponential decay or even faster. Whereas if you have covariance functions that decay much slower, say linearly, then we call that a long memory process. Okay, and there's a lot of interest in the literature of knowing what happens to long memory as well as short memory. So what's nice about this class of models is you can allow for short memory and long memory here. Okay, and the best way to tell whether it's short or long, in fact, you could even have it changing from short to long, is to look at the spectral density function around zero frequency. So if lambda gets close to zero, okay, if that goes off to infinity, then you end up with a long memory process. Now, you can also talk about linear processes as well. I won't spend a lot of time about that, but Dalhouse really lays that out very nicely. Okay, so the nice thing is that by making these transformations and writing them down in terms of basis functions, we get a lot of nice properties that are pretty easy to, well, maybe the calculation's not so easy to calculate, but in terms of once you do the calculations, the interpretation for your time series is pretty straightforward. And it means you can think of things in terms of means, covariances, or spectral densities if you want. And in each case, things vary in local time. Okay, so I talked about an autoregressive process of order 1. What about a locally stationary basis process that is AR but of order P? Okay, so this takes a little more work because you have to think about how are you going to guarantee that the functions you write down lead to stationary processes that in a small neighborhood, locally stationary processes, i.e. ones that are in a small neighborhood, are stationary. So the hard part here is to think about how you set the parameters, okay? But the truth is that, if you actually look in the literature, certainly, for example, if you use, for example, R to fit autoregressive time series models, you'll realize that if you look hard, say at the code or even in the help there, that actually, even though you write down a certain model for the autoregressive order P model, and you fit it using, say, the ARIMA function, when it actually fits it inside of R, it actually transforms the parameters first, okay? And the transformation it uses is to calculate partial autocorrelations. Now, I won't talk about how to do that, but I'll just say for the moment that if you make this transformation first to autocorrelation curves, and you model those using a transformed basis function, and then you take the log of the variances and you write those in terms of basis functions, then that guarantees local stationarity. And we talk about that in our paper. So the point here is to make sure that you're always stationary, right? That things aren't blowing up. Now, once you realize you can do autoregressive processes in this way with a locally stationary basis transformation, you can go crazy, right? And in our paper, we talk about lots of models. So we talk about you can do moving average, you can do autoregressive moving average, you can add in long memory, so you can do locally stationary fractionally differenced, locally stationary exponential. If you want to mix it all up together, you can do autoregressive fractionally integrated moving average. Okay, time series just seems to be putting more letters on the end of a time series model, right, to make it more complicated. But what's nice about this is that you can take lots of classical time series models that we understand, okay, and through a basis representation, allow these models to now slowly vary over time, right? So that's the real advantage of this approach. The other advantage here is that we're going to be parametric, okay? So we're going to have to write down some basis functions to try and express what's going on, and then we can start to think about statistical inference that comes out of that. Okay, now before we get there, let's look at an example of a spectral density function. So here's the spectral density function, okay? And the spectral density function, if it was stationary, we would typically write in terms of frequency. Okay, so for the moment, what I want you to focus on is just what happens in the margin here, which is when rescale time is 0. So if you look at this, and I know I'm not going to do anything fancy like spinning around the graph, but you can see what happens. So we basically have the spectral density function starts here, it goes up to a peak, and it comes down. Okay, now this is one of the behaviors that you see for an autoregressive process of order 2. Okay, and what basically happens is at a certain frequency, we're seeing a lot of contributions of dependence, right? So that says that there's something going on that's almost like a sinusoid, okay, but it wiggles around a lot, okay? So we call that in time series analysis quasi-periodic, okay? And so what this basically says is that you basically have a signal that kind of wiggles around with a certain periodicity, right? It's not exactly seasonal. It's got some noise in it, okay? And, people have looked at this for a long time, these sorts of models. I mean, AR2 is a good example, for example, of counting sunspots on the sun, right? People have modeled this since the 1700s, right? So this characterizes a certain sort of correlation structure. But let's imagine now that I went from a model that starts with this sort of quasi-periodic structure, right? So basically something that is randomly, close to seasonality. But then imagine that seasonality disappears, and then we just end up with something that only depends on what happened the time series point before. Okay? Now, hopefully that's not what's happening in the sun. You're not getting some structure and then suddenly everything dies, right? That would be very sad, right? But, you can imagine a process where you might see certain structure that, through some modulation, of the engineering, maybe, this is looking at engine noise and then things might calm down. Okay, and so in this model here, we basically move from an AR2 model, so something that has a lot of dependent structure, to something that's much simpler, that's AR1. Okay, and you can define this very simply using basis functions. So this is an example of an LSB AR2 process. Okay, now, how can we estimate the parameters? Well, everything is written in terms of these basis expansions, in terms of these coefficients beta. Okay, so you can write down, certainly in the Gaussian case, you can write down a likelihood function and then a log likelihood function. Okay, you can exactly write things down in terms of prediction errors, which is a common trick that we do in time series analysis. So if we write things out in terms of one step ahead predictors and one step ahead prediction error variances, okay, then it's a lot easier to write down this likelihood function. In our paper, we show that you can actually extend something that people do to stationary time series, which is called the Levinson-Durbin recursions, to actually do this time varying. And so what's really nice about this is that you can go through something you would classically do for any time series model that was stationary. And now, as long as you evolve it over time, you can basically calculate the likelihood, okay, for these processes as well. Okay, and then you have to solve these equations numerically. So we use the BFGS solver. Another method that people use for time series estimation of parameters is called a Whittle estimator. A Whittle estimator says that rather than looking at the data itself, we're going to take the Fourier transform of our data, okay, and calculate basically an estimate of the spectral density function. Okay, and here's one example of a spectral density estimator. It's called a tapered periodogram. Okay, and it's an estimate of our spectral density function. We're going to call it a local tapered periodogram because rather than just estimating in frequency, we're also going to estimate in local time. And so that leads to something called a Bloch-Whittle estimator. So the basic way that you think about that is that you imagine going through blocks of time, and in each block of time, you're going to take basically a Fourier transform of your data, and then you're going to try to estimate the periodogram, your estimate of the spectrum, and then you're going to evolve that through time and then form a likelihood out of that. Okay, and in the stationary case, Whittle log likelihoods are asymptotically equivalent to Gaussian likelihoods. But when you get to small samples, that doesn't have to be true. And certainly in the non-stationary, local stationary case, that certainly doesn't have to be true. And so there's a question about whether these estimators, although they can be computationally a lot more efficient for lots of processes, they may not be as efficient an estimator in practice. Well, in our work, we looked at asymptotic properties, and already there's a lot known about locally stationary processes. And the question is, whether, under the conditions that we've put down for our processes, does that guarantee that you can work out the theory for these? And thankfully, the answer is yes. Okay, so even if you have short range dependence or long range dependence, you can see that if you use the maximum likelihood estimator, or indeed the Bloch-Whittle estimator, okay, you get consistent estimates, you get asymptotically normal estimates, and we can work out what the covariance structure looks like as well. You can also show that things are asymptotically Fisher efficient. So what's nice about this is it tells us that certainly we can use either maximum likelihood or these Bloch-Whittle likelihood estimators, okay, and we can do inference based on that. Now, just to push you a little further in thinking about this, as much as the parameters are interesting to us, they're maybe not the only thing that I care about. If I go back again and talk about the representation, okay. So remember, here's the beta. It's hidden away through link functions of linear combinations of basis functions, and then that links all the way back to my transfer function, okay? Well, if you think about it, as much as I care about the betas, I also care about lots of other things, right? I would care if I didn't have a non-zero mean, I would care about the mean function. But I certainly also want to understand how the spectral density or the covariances change over time. So if you notice here, I've been very careful to put the betas everywhere. Do you see that? Betas, betas, betas. And so once you have these asymptotic results, it also tells you that you can actually start to develop asymptotic results for time-varying spectral density functions and time-varying covariance functions. And so it's not just that we're going to do statistical inferences on the betas themselves, we're also can do inferences on the spectral density function and the covariance function as they evolve in time. And so that's really useful, I would say, in building a toolbox where we can start to think about how we do inference. Okay, looking at my time, I've got to make some decisions about what I spend some time doing. So there's a few things that we sat there thinking about. One was just to see how well our estimators do with simulation. I won't spend too much time doing that, but I will tell you that we're not the only ones who write down locally stationary models and estimate them. So Palma and Olea also developed an estimation method. They used Whittle estimation, but they didn't do transformations of parameter curves. So they just say, forget about the link function, okay? And we'll just take a time-varying function of basis functions. Now, at that point, you have to be far more careful to make sure the process is stationary, okay? And so that's something you have to watch out for. And it's not always guaranteed that this R package guarantees that. But it's a good place to start just to see how well we do compared to this, okay? So notice here, they're using a Whittle likelihood-based approach. And I've already hinted that it may not be as efficient as what we do. So let's have a look. So I'll just show you an example. This is for the autoregressive 2 process I talked about before. And all we're going to do is I'm going to look at the integrated root mean squared error of the AR1 parameter curve estimates over time, over local time, as a function of log 10 of how big our time series are. Okay, I'm also going to do the same for the AR2 parameter curve. And then I'm going to say, well, I can also estimate the time-varying log spectral density function. So how well do I estimate that in an integrated root mean squared error sense as well? So as you can see, looking at the scale here, the triangles in gray are the Palma method, and then you can see that here's our block Whittle, and then here's our maximum likelihood. So maybe it's not a surprise, and I'm not really trying to ding Palma and Olea. I'm just saying that, depending on what methods you use to estimate, you can do a lot better in terms of estimating these parameters. Okay, now all of these parameters we've shown are, asymptotically unbiased, in our simulations, or they seem to be, and then they have other nice properties as well. But at least just for the moment, this gives you a feeling, right, that these parameters are doing the right thing. And as their sample size increases, indeed, the root mean squared error in an integrated, right, over time gets smaller, and the same when we look at log spectral density functions. Now, in our paper, we have lots more simulations to do with estimation, but I just wanted to give you kind of like a quick summary of what happens there. Let's talk about other things that you want to do in time series, right? So life isn't just about parameter estimation. It isn't just about uncertainty quantification. There's other things that you would want to do. I'm a big fan of looking at my time series and exploring and thinking about what happens here, okay? And what's really nice about local stationary processes is that we can sit there and we can take time-varied Windows versions of sample statistics to carry out exploratory data analysis, right? So just like if you were in a stationary process, you might calculate the autocorrelation function, or you might calculate the partial autocorrelation function as a view of the dependence in the process. Now, you can do this windowed in time as well and use that as a way to start to decide how you're going to model the evolution in time, okay? Do I need an autoregressive process, maybe moving average parts? A lot of the stories that you might learn in an intro time series class also applies to these processes here. You just have to now let things evolve in time. What about model selection? Well, we didn't push this very hard. We did think a little bit about AIC and BIC, but the most common one that you see in the literature for locally stationed process, again, is due to Dalhouse. You'll see that name has turned up a lot, of course, who uses what's called the non-stationary information criterion. That looks almost, I mean, basically like an AIC, but there's an adjustment for sample lengths. And when we looked at that, that seemed to do pretty well in terms of our applications. There's lots of other things you might want to think about. You could consider, for example, Bayesian methods, putting priors on the parameters. You could also think about, lasso type methods to penalize. But we haven't actually thought about any of that. We just said, well, if you go with a classic maximum likelihood based approach, what would you learn? And then you can also do forecasting. And what's really nice about the forecasting is that, remember I said before that when you calculate the likelihood, okay, you do this through time-varying Levinson-Durbin recursions. Sorry, I'll just be a second. So there's a very efficient way to calculate the likelihood function. What's nice about that is if you calculate these coefficients that evolve over time, you can also evolve them from the end of time under suitable approximations to also do forecasting into the future. Now, forecasting into the future when you have something locally stationary does require some assumptions that you have to make. Okay, in the simplest case, just think about it. You've basically modeled over rescaled time. And the question now is to say what happens if you go outside that rescaled time. And that seems a little strange, right? Because that's what the model does. So what you basically have to do is you have to make some assumption about where these basis functions are going to go in the future, right? And if you do that, then this method, it works well. There are slightly more complicated approaches out there where you change the asymptotic slightly, where you imagine, maybe there's rescale time, but also time can expand. So we call those mixed asymptotic regimes. And I think you could think about forecasting in that sense as well. I've seen it more in spatial settings, but less in time series settings. But I would imagine there might be something you could do there as well. Something else that we thought about is, can we test whether or not we need this locally stationary process rather than a stationary one? So I won't go through all of these different methods, but there is a lot of work that people have done to test for departures from to test for stationarity or non-stationarity. In our approach, we go a little simpler, right? And what we're just going to say is, does it seem likely that we need a stationary model or the model that we fit? And we're going to do that through a likelihood ratio type approach. So I can explain that fairly simply. If you just look at the transformation of your parameter curves, imagine that there's an intercept plus a whole bunch of things that depend on your basis functions. Okay, now if you think about it, the basis function part encapsulates the changes over time, right? Of course, the intercept doesn't change over time. So what we're basically going to test is whether or not we need all these coefficients here. Okay, so we're going to test whether these coefficients here in the sum for each of these basis function representations are zero. So you can do that through a likelihood ratio statistic, and you can get a chi-square distribution. And we've looked at it in terms of power calculations and checking the size and everything, and compared to the most famous non-parametric test, we do better. Now, that's not a surprise, I would say, because number one, we're parametric and they're non-parametric, so they can find more departures than we can. But certainly what it says is that, say, if it was an AR1 model where the autoregressive structure changes over time, the question would be, could you detect it? Okay, and our answer is yes, we can. Okay, and certainly as the sample size increases, it's easier and easier to detect that you need a non-stationary model. Okay, so I've talked a lot about, writing down the models, starting to think about different inference methods we can do, everything from estimation to uncertainty quantification to forecasting to model selection to checking if we need the model at all. Let's try and apply it to an application. Okay, so we're going to look at, I'm not going to pronounce this, I'll just say EEG time series, right? And why do we collect an EEG time series? Well, basically it's a non-invasive way, right, to monitor electrical activity in the brain. Okay, and it basically is a way to look at brain health, right? And so what we know is that certainly there's going to be lots of stimuli, stuff going on inside the brain and stuff going on outside the brain. So we don't expect brain characteristics to be constant over time. And so stationarity might seem like a poor approximation. Okay, so in fact, even going back to 1973 onwards, right, people have been thinking about ways that, you know, the model might be non-stationary. And very often people will use a windowed spectral or wavelet analysis to analyze these data, but I'm not saying it's impossible, but it can be a lot harder to start to quantify the uncertainty, okay, using these tools. Okay, so the question is, can we do better with a locally stationary basis approach instead? Okay, so I'm going to look at an example. This is a pretty famous time series example. So these are for a subject going electroconvulsive therapy, ECT. Okay, so this is a treatment for patients with severe clinical depression. Okay, it comes from West et al. Back in 1999. They had 19 series. We picked one of the series, okay, that West and co-authors have also looked at in their time series book. And what we get is this EEG time series measured in millivolts over seconds. And you can see things are sampled very quickly. It's 256 observations per second. Okay, we've got about 14 seconds of data. Okay, and I don't think you need to do a time series analysis to see that the properties of the time series are not constant over time, right? Okay, and it's not just that the variability seems to change over time. If you certainly see the ability of the wiggles, right, you can see basically these oscillations that aren't quite perfect oscillations, right? They're a bit random, bit autoregressive type structure in that's changing over time as well. So people certainly have looked at stationary models, but I don't think that would be the case here. And in fact, when we test for local stationarity, whether our model's preferred over a stationary model, we prefer that by a very, very small p-value. So small, I haven't even put it in the talk. So what would be the simplest thing you could do, right? So if I look at panel A here, this is what people would do if they just do a raw estimate of what's going on. So they're going to calculate this tapered Fourier transform in windows of time, okay? And as you can see here, this shows you where I have a lot of activity, okay? That's in red or orange, and then the blue is less activity. Okay, we're looking at the activity over different frequencies. Okay, thank you, as time goes on. Now, people already know a lot about brain activity, and they've already split things into different brainwave bands. So there's delta, theta, alpha, and beta. Okay, and even in this one, which is a very rough estimate, you can see that what happens is there seems to be activity here in the beta band, okay, where the frequency of that seems to change over time, and then it crosses over into the alpha band. Do you see that? Okay, so you can certainly see that there's a peak around 22 hertz in the beta band, okay, but it moves over to the alpha band. Okay, so B and C is what we're going to do. So we sat there fitting lots of locally stationary basis AR processes of lots of different orders. And this model is very complicated. I'll tell you that I'm not showing you the entire picture here. I'm just showing you part of the frequency bands, the ones that scientists care most about. And when we pick a model, we end up with 19 AR coefficients now that must change over time, and then a variance that also changes over time. Okay, so if we do that, you can now see from the parametric estimate, so this is our smoothed estimate from our parametric model relative to this, okay, that we get a much cleaner signal of what's going on. Okay, and so indeed it does clearly show that it goes over here, but you'll actually notice here in this part, it says that it's pretty hard to say whether it's really that strong at the end at all, okay? Whereas, you know, there's a bit more uncertainty here, a bit more noise if you just look at the raw. What about part C? Well, part C is that when we use a parametric model for estimating this time-varying spectral density function, we can also quantify the estimate, the uncertainty. Okay, so in addition to me giving you an estimate, I can also give you a standard error. Okay, and so you can see that for a lot of the space, it's quite, we're, you know, pretty low uncertainty, and there's more uncertainty around the peak. Okay, but you can actually see that in some places you're very sure about what's happening. Okay, and we can do that very easily using the asymptotic results. Okay, so this hopefully gives you some demonstration of the ideas of what the approach does. So our argument here is that locally stationary basis processes allow for flexible modeling of smooth departures from stationarity in time while maintaining statistical efficiency and ease of estimation. On purpose, we've built the models by thinking about what happens in a stationary context and really building these basis functions through a transformation that allows you to really understand what's going on as you go through time. Okay, and we can do likelihood-based parameter estimation as possible. Okay, it also allows for uncertainty quantification. And by nesting the stationary model within the locally stationary model, okay, we can also do tests for stationarity. So does it seem like it's stationary, or should we be using our approach? There's lots of places you could go with further work in here. We haven't spent a lot of time saying, well, if the data generating model is this and our model is this, how badly do we do? So we do care about model misspecification. As Yao had said at the start, I do care a lot about non-Gaussian processes, and this isn't clearly looking at that. And, you know, when you look at non-Gaussian time series models, they have a very different flavor. And so part of it is understanding their flavor before you go and write down models in this way. Okay. And then currently we're finishing off work where we're pushing a little further than what we Shrena did in the dissertation to look at rescaled time and rescaled space. So to do spatial-temporal modeling. And at that point, that allows you to do spatially varying basis functions. And so I'll finish there for just now. And I put in some references as well. Thanks a lot.
Thank you, Dr. Craigmile, for the excellent talk. We'll now open the floor for questions. So please raise your hand or enter them in the chat, and feel free to briefly introduce yourself as well if you like. Yes, Abhinav.
Hi, this is Abhinav. I'm an undergraduate student at UConn. First, thank you for the presentation.
You're
So I
welcome.
kind of had two questions.
Yeah.
So in your EEG example, you mentioned doing both a formal statistical test and visualizing the data to see if it's stationary or not.
Yeah.
I was curious to know, like, if you're analyzing a new data set, are those two methods enough to go forward with non-stationary methods, or are there any other things you would want to check?
Yeah, so in the paper, I would say that the test is a little, so ours is not a general test in the sense that a lot of other people have. So you do have to think of what the locally stationary basis process is first, and you have to fit it before you can carry out the test. So maybe I misquoted exactly how I would use it, right? So in practice, what you would do and what we do in the paper, and I think most of that part sadly is in the supplement, as life always goes, right? It gets thrown away somewhere else, right? In the depths of time. But what we did first is we actually looked at graphical summaries like this one, but also looking at time varying autocorrelations and partial autocorrelations. And from that, we could see that the structure was changing through time. And that gave us an idea about the autoregressive models. knowing what we know from stationary models, it also told us that it didn't seem likely that it was a moving average, and it didn't seem like it was long memory. And so I was doing a lot of exploratory, or we were doing a lot of exploratory data analysis first, before we then thought about the structure of the models. The other thing you have to think about is the basis functions you're going to write down as well. And we did play about that for a long time, but then we realized it was taking away a lot from our discussion of these models. So for these, we actually use B-spline basis functions, but you could use other basis functions as well. And I guess you could try to explore that as well by using your raw estimates from the data. So I think the bigger story is explore the data as much as you can first, then consider classes of models you're willing to entertain, then fit those models. And then as a check at the end, you can do the test to see whether you preferred it to the stationary model.
Yeah, that's definitely insightful. Kind of a related question. So you also mentioned that you compared your test to a non-parametric test and your test performed a little bit better. You also mentioned that the non-parametric test captures more general departures from stationary. I was just wondering, like, could you expand on that and what you mean by that?
Yeah, so in our test, we're just saying, look, I fit my model versus the model which is stationary, right? And the question is whether I prefer, if I'm under the null model, I'm stationary versus rejecting, right? But if you think about that, you're always fitting the locally stationary basis model at that point, right? The Paparodis test is purely based on basically integrals of spectral density functions. And it doesn't care what the models are, right? It just says, take a spectral estimate from the data, allow it to evolve in time. And, there's a little bit of work about how you do the test statistic. And it's not an easy paper to read, I will say. But you go through there, and under the right conditions, it has certain properties, and you use that test. And so at that point, the null thing is to say it's stationary, i.e. the spectral density function doesn't depend on time. But there's lots of other things that could happen in the alternative at that point. Whereas ours is just saying, look, I'm doing it within my model. So yeah, it's more limiting in that sense. So I don't want to give the idea that Paparodis is a bad test, because you can see it does very well, for detecting the change. It's just that, if I basically put in something that's so well controlled, right, then I'm going to do better, right?
Yeah, that makes a lot of sense. Thank you for your insight.
You're welcome.
I see there is another question from Deborah Priya. Sorry if I mispronounced. So her question is, you use Fourier transformation. So how do you understand that you need Fourier transformation in here?
So the truth is that, you could get away with never having to take a Fourier transform if you wanted, right? A lot of people just spend their life in time series analysis modeling covariances, right? And I would say that these models could be viewed as looking at how the covariance structure of a time series changes over time. The Fourier transform is an extra tool in your belt that allows you to basically say, there's another way that I can understand dependence. Because if something is stationary, then you can always look at the covariance or the spectral density function. And so what you'll notice is for certain people, especially, if you're in signal processing, okay, and maybe another good example would be like earth sciences, geological sciences, things like that, areas like that, and then medical as well. People are very comfortable doing spectral analysis and doing this Fourier transform. And so I will say that, I was lucky, and I spent a lot of years, I took a course in time series, then I took a course in Fourier methods, then I took a course in wavelet methods, right? And so you kind of build up these tools that then say, look, there's many ways to view a time series, and maybe different views give me a different idea about what's going on. And so the Fourier transform here, is just another view, right? You know, it's just another opinion. It's like having two newspapers to tell me about the news rather than one newspaper, right?
Great. Any other questions? So there's another question from Chang Lu. Her question is, the EEG example looks like a denoise process. Are time series applicable to signal denoise?
Yeah. I mean, that's a good way of thinking about it here, is that what you're trying to do is come up with a denoised view of the time varying spectral density function. And this is one way that you could estimate it, right? With an uncertainty of what's going on here. What's funny here, I mean, in these things, I mean, the truth is for EEG, most of the time people care about the spectrum, right? And why? Because they've already said they care about alpha, beta, theta and delta, right? And so at that point, people are viewing it. People don't, I mean, as much as I drew the time series plot to give you a feel that something's changing, I don't really want to denoise this process, right, on this scale. It is true that I want to denoise on this scale. So yeah, I mean, it's a way to view what's going on. Yeah, that's right. Yeah.
Great. So I think now, we have one more question. So yeah, so that should be the last one before we wrap up. So this is from Nicholas, and he is taking my time series course this semester. So his question is, do LSB models have similar overfitting risks to other models, or are those risks addressed by the NIC or other techniques?
Yeah, no, I mean, that's a perfect question. Yes. All time series models, parametric models have this problem where if you allow them to get larger and larger, then you definitely will overfit, right? And so you do have to think about ways to mitigate it. The Dalhouse solution is to use NIC, which is like, basically a locally stationary analog of IK keys, or Akai key, depending on how you pronounce its information criterion, or the Bayesian information criterion. But we also know that those methods aren't always that robust either. And so, there's still a potential for overfitting. And I think it'd be interesting to look at other ways of thinking about model uncertainty, right? Maybe Bayesian or something like that. Yeah, great question.
Great. Now we're going to wrap up the first hour technical session, and then I'd like us to take a short break, like 1 or 2 minutes to drink water and stretch and maybe get a coffee before we move on to the next 30 minutes virtual coffee session. So we're going to kickstart our virtual coffee session. And here to encourage discussion from different perspectives and help us get started, I've invited a special co-host today, undergraduate student Abhinav, to kick off the conversation. And in the meantime, we'd also love to invite anyone in the audience to contribute questions or comments, whether you're a researcher, practitioner, or a student. The questions can be non-technical or technical, or any general questions. Please raise your hand or enter yourself in the chat. So as we are waiting for more audience questions, Abhinav, I will hand it over to you.
Yeah. First off, thank you again for the webinar. I found it really interesting. So like myself, a lot of undergraduate students are interested in graduate school or doing research in the future. So I'm curious about your background. How did you know graduate school was right for you, and how did you know that you wanted to become a researcher?
Yeah, that's a great question. So I'll just say, I started pretty far away from America for my undergraduate. So I was in Scotland, and I had in those days, they were already running bachelors in statistics. So I was doing a bachelor's in statistics and math. And so we had a fairly large exposure to different statistics courses, which is certainly something you guys seem to have as well. And so I think that helped me in a bit, because it certainly gave me a view of lots of different things that people do. Okay, rather than just, maybe everyone has a math stat course, a regression course, and an introstat course. So seeing different things is useful. That's the first point I want to talk about. The other thing is just talking to people and getting research experience, right? And this is all over the news nowadays, right? All over universities, right? About how valuable research experience is. But for me, it was important. Certainly, when I got to going between my junior and senior year, I found a professor to work with in the summer, and we worked on a very simple project, right? It was basically to work on if you had two uniform distributions and you mix them together, what happens for parameter estimation, right? And but it was a way where I got to practice lots of things, everything from a bit of computing, a bit of LaTeX, and and trying to hone my math skills, which were still needed lots of work, right, at that point. And then it was a pretty short summer project. And then I got to work in a biostatistics group where they were basically having me check over someone else's modeling for generalized linear model calculations. And I did that as well for the second half of the summer. And at that point, I think I kind of understood that interested me, that that was what I liked. Along the way, I had taken various internships at other places, like I'd worked for the government, or I had worked for an insurance company at one summer. I couldn't quite get to see what the actuaries were doing, but I was doing some boring job in an insurance company I could see from afar. And I think that just it taught me a lot of things about what people do, but it also said maybe that grad school was what I wanted to do. And so I think the other thing is just talking to people and finding out what opportunities there are. And that helps a lot. Yeah. Get that. Yeah. Don't feel scared about asking questions. Yeah. If that's something that interests you. But yeah.
Yeah, it's definitely interesting and useful to get a variety of experiences. Just to kind of follow up, like if you were to, talk to an undergrad or somebody considering a PhD or a master's, like what skills or experiences do you think were most helpful to you beyond maybe coursework?
Yeah, it's just great timing. So yesterday we had our graduate fair at Hunter College, and so people are coming by asking, what skills they should have to come in and do the master's program. And it's kind of a boring answer for a lot of statistics graduate programs, and the same for data science programs at the moment. As much as it's great to have lots of experience of statistics, I think very often it's your math skills that they're going to look at for first, right? So I would say make sure that you have plenty of experience and you know how linear algebra works, plenty of experience of calculus, multivariable calculus. And if you know what a proof is and you've seen a little bit of analysis, that's going to be really valuable as well. And that's a little bit of a boring answer, right? So the answer is if you want to do more stat, learn more math, right? But it's a really good piece of advice. And if you apply to most programs, they're going to look at that first before they look at the other experiences. Now, that's not to say the other skills aren't there. I think we want to see people have independence, right? And so doing a project is a great example of that. Maybe it was a project in a class, maybe it's, summer research experience. And then the other thing is just, kind of a flexibility to learn new things, right? And try out things. And, very often that could be in what choices of courses you've made, or it could just be, what other things you've decided to do with your time, right? Things like volunteering and doing stat and things like that has become something that people didn't do when I was your ages, right? And those are things as well. But certainly, I'll circle back around. I think the math skills are the most important part. It's great to have lots of exposure to statistics and then realize that, when you do it at the master's and PhD level, you're going to see some of this stuff again, but it's going to be more formal and more mathematical. And so it's good to be ready for that. Yeah.
Yeah, I agree. I think a lot of people share your sentiment. A lot of people have told me, just study more math and you'll be better off. That's interesting.
Yeah, at Ohio State, when I'd have students going off for PhDs there, I would often talk to a student who was in their senior year, and I would see what they'd taken, and they say, what stat courses would I take? And then I was normally like, let's see your transcript and let's work out what other math courses you're going to take. Sorry.
Yeah. So to kind of pivot to your research a little bit, reading your bio, you work across many different fields. Even in the paper, you mentioned how a lot of different fields lead to non-stationary data. I'm curious to know when you're approaching maybe a new field or working with a collaborator from a different field, what's your approach to like getting up to speed and getting that domain knowledge that may be important?
Yeah, that's a really good one. So I think the most exciting thing that I do is get to collaborate with people, honestly. I mean, I get to learn science from other people, and then we, apply statistical methods and think about how statistics can help. I've worked in teams where it's just me and someone else, or, you can have lots of people, maybe too many people, right? All on the same project. But I think it's important to realize that an interdisciplinary project is just that, right? That people are bringing lots of skills to bear to try and solve a problem. And so I think it's really important for you to stop and listen and understand what people are telling you. But at the same point, you're not going to understand everything, right? So I remember, I don't know, maybe it was 10, 15 years ago, there were somebody who started working with an atmospheric chemist. It wasn't me, right, at Ohio State. And they decided that to learn more atmospheric chemistry, they were going to sit in the professor who they were collaborating with's class about atmospheric chemistry. And they learned very quickly on that this was a very bad choice, right? Because the amount of prerequisites of chemistry you needed to get to understand how atmospheric chemistry works, right, in the upper atmosphere was really hard and really complicated, right? So number one, you don't have to understand everything. That's the major point I would do. But at the same point, you have to understand something, right? And you have to understand what is going on and what's not going on. One of my first collaborations was looking at hearing tests for children. So every child that is born in the US has to do this test for hearing. And as you can imagine, a baby can't hear, right? Can't say, I hear you, right? And so you have to think of a non-invasive way. And there's a test based on a spectral density function. And so someone came to me and they said, this is what we do. Okay. And how would you do it, right? Can we work together? And, you learn about what they do, you learn about why the physics works, and then you go through and you look at what they do and compare it to what you do, and then you see if you can write some stuff up. And the interesting thing you learn along the way sometimes is that people have been doing things in what you think is a weird way, right? And then you look at it and you go, well, actually, that works pretty well, right? And sometimes the statistician's job is to say, well, why does it work well? Can we work out the theory for that? Is there a reason for what it does? But yeah, make friends with people, but listen to people, think about what they're doing, and think about what you can bring to it as well. Yeah.
Yeah, just to kind of follow up, were there any fields that, at first glance, you wouldn't think to use the same statistical methods, but, going deeper into it, you found a lot of similarities?
Yeah. And I think it's very hard sometimes to get into literature from different fields because you're not reading those papers, right? You're very often reading stat papers, or you might read papers from a few disciplines and you don't see what's going on. And so there are these bits where you just don't know what's going on, and maybe they don't, right? But I think it's interesting to notice how, there are lots of smart statisticians working in many fields, right? And they're not called statisticians, right? They're biologists, they're ecologists, they're geneticists, right? I went through biology there, but you could do the same with other disciplines, right? Computer scientists, whatever. And Yeah, I think it's really surprising to realize that lots of methods can be reinterpreted in lots of fields. You know, principal components is the most famous example of that, where it turns up everywhere, it has different names, and it's very useful, right, for understanding what goes on. I think you have to realize that, and just realize that some disciplines appreciate statistics in certain ways because their statistics developed in certain ways. So like if you look in psychology, for example, you know, mixed effects modeling and longitudinal analysis is probably the major thing that they think about, right? Whereas, you know, hydrology, for example, time series modeling is huge, right? It's a big part, even more so than, you know, maybe some other areas, right? Where time series could be used and is never used. Yeah. So it differs by the discipline. Yeah. It's very interesting to see what people do. Yeah. Astronomy is a real confusing one. Yeah. Some of their approaches are very different and unusual from what we're used to, but it's changing very fast. It's changing at a very fast speed. Yeah.
And again, a little bit related question. Are there any fields that you yourself have done work in that maybe you think is a little bit underrated that some statisticians won't really touch, or
Oh,
you know?
yeah, no, that's true. I mean, I think there's always this argument that, you know, somebody's dabbling in an area and nobody else is working on it. I think very often that's untrue. Um, you know, like so for a while we had a project. I spent a year in Glasgow, and we had a project looking at basically measuring magnetic fields around the Earth, right? Um, and so why would you do that? So you're looking for storms from the sun, solar storms, they're called. Okay. And they have the ability to basically knock out communications around the Earth, right? If you have a very large storm. And, you know, we thought we were basically developing all these stat methods and there weren't too many people working in the field. But then you just fast forward a year and then you realize there's a whole bunch of other people working on exactly the same problem, but they just didn't talk about it, right? And it's hard to tell because normally they're not publishing in stat journals, right? So you don't see it unless you accidentally hear a talk or something like that. I'll be honest, I think that if there's an interesting statistical problem and some good science to solve, I'm happy to work in any field. And I think anyone would be happy to work in any field, right? In that way. I mean, you know, there are historians out there, right, who are doing statistical analyses, right? And you know, and some very interesting questions about what's going on, right? I'm currently working on a paper with not a historian, but it's very historical about, you know, for example, there's a very famous polar expedition that failed, right? And people died and all this. And the question is why things went wrong, right? And you can look back at the data from the past and try to understand if you can reconstruct what the climate was like, right? To maybe say a story about what happened. So anything could be interesting. Yeah. Yeah.
Yeah, that's pretty interesting. So I had a little bit more of a general question. So you see, like research can be pretty difficult. And so a lot of research is making small incremental improvements onto a field. Um, and so a lot of students, uh, they may be thinking of like a big picture impact. And so that can be a little daunting. So what's your kind of perspective into like organizing your projects? And I know it can be uh, difficult to decide like what's actually important or not.
Yeah. I tend to be a little easy on myself and maybe a little easy on my PhD students because I'm not a big fan of writing down the most complicated model first and then trying to solve that problem. Okay, so I mean, for example, in the talk I just gave, I could have said that the first thing I want to do is do spatial temporal modeling, or I want to do it for multiple time series, you know, at the same time. And on purpose, I try to make things a little more constrained first and then solve that problem first. And then if we have time, we get to more complicated. And I'll be honest, my feeling is that's not common nowadays, that people will tend to write down a much more impactful, more complicated model first, right? That tries to solve a much harder problem and then go through it. But I like the idea of kind of having building blocks and going and working my way through. And so, that's maybe just the way my brain works. I like to think of smaller problems and then from what I've learned to go up. And problems don't scale, right? It's not like I solve this small problem and then immediately I know how to solve the big problem, but I like to think of it that way. What I will say to you is that, for students going and doing PhD, that may not be your experience either. I think the other thing that's worthy of remembering, anyone doing a PhD, you're driving the research, right? But you have an advisor who's going to give you advice. You're going to see a lot of variability about what that means, right? Some advisors will get their hands dirty, others will not, and some are proud of not getting their hands dirty because they're just advising you and you're doing all the work. So I think partly it's on you to think about how you like to work and learn, right? And then to go through. I think the important thing at the start is also to know what's been done. And so people often can be lazy about literature reviews. I know I am, right? And then you don't realize that someone already did something. So that's just as important, I think. Yeah.
Yeah, thank you. So just to kind of pivot to maybe a more interesting topic. So obviously we live in the age of AI and LLMs. So you
Yes.
see articles of people using it. It's integrated into many different products we use daily. And so, recently read an article about a researcher who not only used it as a tool in like transcribing and note taking, but also used it as like a collaborator for research itself. So I'm curious to know like your perspective on AI and LLMs. How do you think it'll impact the future of research?
Yeah. It's already impacting it. I mean, if you go to the joint statistical meetings, it seems to be the only thing that people are talking about. There's all these, important sessions of the national academies and things like that, trying to work out what its impact is upon society and what its impact is upon science, right? And how we do science. And from talking to lots of people, because we are all talking about it, right? People realize that there's something to learn from it and something to do. Personally, I'm a fuddy-duddy and I haven't got very hard into it, right? As much as I casually look at it to understand what I think it can do at the moment, right? But I'm well behind the times on that relative to some other people, right? Lots of people are, yeah, it's a friend and it's trying, whatever friend means in that context, and it's trying to help them do things. And I certainly see and I listen to what people do with it, and I understand what it can do for you. Simple things from giving me a different view of how I wrote something to, as you said, that one I didn't even think about, but it doesn't surprise me about being my collaborator, right? So, I mean, it's a tool, right? It's a tool like anything. And I think you have to understand what is it that the tool is giving you and what is it that the tool is not giving you, and what can you believe and what can't you believe, right? Just like with any tool. And I think that's the part that we're kind of in buzz phase at the moment, right? Where everyone's like, right, it can do this, it can do that. And I think there's no question that, it's here to stay and we can't ignore it, right? I think the question is to understand what its roles are in what goes on. I think it's very interesting to see if you, from talking to people who are teaching statistics, how many people have embraced it as a tool that students have to use to solve certain problems in class versus some who say you're not allowed to use it, right? And I think that's already quite indicative of what's going on, right? That things are interesting about what goes on. There are some interesting places where I think statistics may become less useful as well. I mean, some of these learning techniques, like image learning and things like that, I can say there's some big projects that I work on where we do waste an incredible amount of time, right? trying to get the data right before we even do the analysis. And I always joke to classes, it's like, I don't know, 70, 80% is getting the data right. And, 10% is the analysis, 10% writing up or something like that. But yeah, I mean, I would love to know, let's fast forward 5 years to what it does for, us starting to collect and check over data sets. They're very complicated. That to me seems like a good place I might start. Yeah.
Yeah, thank you for the wonderful questions from Abhinav. So to wrap up, I also like to ask some questions from my perspective, especially given the last question is about like using different tools. Like today's talk is about spectral domain analysis for time series. Like from that point of view, so actually we have even for statistician mathematicians, we have a lot of different tools for analyzing time series. For same problem, we can do it in a time domain or frequency domain. And nowadays we have different algorithms from the AI domain. So I wonder, I'm curious about your take on future data scientists, right? There are so many tools available, right? How do they get, what's your suggestion on like how to get started? Like given the question, like given a data set, where should we start?
I think especially if the first thing you ask me is, are you interested in doing good prediction, right? So if that's the first one, if the learning is about prediction, then I think, it might be quite naive to think that a lot of the models we're writing down are the ones that people are really using day to day nowadays, right? I mean, there's little question that machine learning, statistical learning techniques are, if you go into companies, those are the tools that are being used, and large amount of computing power is being used to go through for insanely large numbers of time series, right? To do predictive analytics, so to speak, right? Or to choose what I should put in my portfolio or things like that to minimize risk. So I feel like there's still a bit of a disconnect there where, we're doing some fairly simple modeling and they're doing some, I just don't care. I'm going to just throw it all into a model and try to understand what's going on. I'm very interested at the moment by the people who are building models that are statistical in nature, but use these as a part of the model, right? These neural nets and things like that, or convolutional neural nets. Because I think that's really key for us to think about how we connect what we do to what is being done already, right? In a more statistical framework. And I'll be honest, I don't know enough about that yet. And but there are a lot of cool people working on it. And I keep telling myself I'm going to read all those papers and learn more about what's going on. But I'll be honest, I haven't got very far yet. And maybe I can just cheat and say I'm a bit older and other people are going to do that anyway. But yeah, I mean, it's always funny to see every decade there's a different theme in statistics, right? Or every 5 years, and it's always funny to see, everyone ends up in a fad at some point, right? And then to see where you go after that. I think the interesting one as a statistician is to be able to evolve, right? To smoothly change through time, to be locally stationary, right? To say, here's some tools that I have, and how can I adapt my tools over time? Yeah, keep learning. I think that's the best tool, right?
Absolutely, I totally agree. So it's wonderful to see many young people today joining us, and then so maybe answers will be those will be answered by them in the future, right? So I'm glad that we are all contributing to this the time series community, and then we're exploring it together, finding the answers together. So with that, we'd like to thank Dr. Craigmile for the excellent talk and all the wonderful conversations today. And it's truly amazing. Thank you so much. And thank you everyone for your participation. Thanks, Abhinav, for being the co-host. So hopefully we'll see you next time. Thank you. Bye.
Thank you.